It's fun to be inquisitive. Be nosy, stick to your passion, find out more for yourself. Quest is fun. Join me, Tristan Pang, on a journey of inspiration. Welcome to Youth Voices. Hello everyone, welcome to my show. This is your host Tristan Pang on Planet FM 104.6 Youth Voices. Great to have your company here today. So, remember last month's guest, Lee? Well, Lee joins me in the studio again today. Hi Lee.
Hey Tristan. Hi everyone.
So, just to remind everyone, you are in Year 12 at Onehunga High School, that's right?
Yep.
So, school just started for a couple of weeks now, so how have you been finding it?
Well actually it's been getting pretty busy, honestly. I've just got a new job at McDonald's, so I've got to balance that.
Well done.
Yeah.
So how's Macca's?
It is people are really nice, but it is
That's
really
good to
busy.
know.
It is really busy.
Definitely being one of the kind of main fast food chains here in New Zealand.
Yep, for sure.
Yeah. So I recently watched a DVD called The Life and Early Work of Ernest Rutherford, which I borrowed from my mentor Andrew Patterson. Ernest Rutherford is a New Zealand-born British physicist who has become known as the father of nuclear physics and was awarded the Nobel Prize in Chemistry in 1908, one of the 3 New Zealanders who have been awarded the Nobel Prize to date. So we kind of set you a little task last time, Lee, to kind of read a little bit about Rutherford. So
let's do it.
Yeah, let's do it.
Rutherford had a very interesting life. He was born in rural Nelson in 1871. Rutherford's mum ensured her 12 children were all well prepared for school and all received good educations. In 1887, Ernest won the Marlborough Education Board Scholarship to Nelson College on his second attempt. Rutherford boarded at Nelson College from 1887 to 1889. In 1889, he was a head boy, played in the rugby team, and, again on his second attempt, won one of the 10 scholarships available nationally to assist attendance at a college of the University of New Zealand. From 1890 to 1894, he attended Canterbury College in Christchurch. There, he played rugby and participated in the activities of the Student Debating Society and the Science Society. In 1893, he graduated Bachelor of Arts in Pure Mathematics in Latin, Applied Mathematics, English, French, and Physics.
Rutherford's mathematical ability won him the one senior scholarship in mathematics available in New Zealand. This allowed him to return for a further honours year, which he took both mathematics and physics. The physics courses required students to undertake an original investigation, and Rutherford chose to extend an undergraduate experiment in order to determine if iron was magnetic at very high frequencies of magnetizing current. He invented 2 devices, a simple mechanism for switching to electrical circuits with a time interval between them which can be adjusted to be as short as 100th of a thousandth of a second, and a detector of very fast current pulses. By the end of 1893, he was an accomplished researcher. In 1893, Rutherford obtained a Master of Arts with double first-class honours in mathematics and mathematical physics, and in physical science.
During his lifetime, Rutherford was awarded scientific prizes and honorary degrees from many countries and fellowships of a variety of societies and organisations. Among other honours, he was elected President of the Royal Society of London and President of the Institute of Physics, and was appointed to the Order of Merit. In 1992, his portrait featured on New Zealand's new $100 banknote.
Rutherford is regarded as one of the greatest scientists of all time, radically altering our understanding of nature on 3 separate occasions. Yet he was no solitary genius, and his success at putting whichever laboratory he was leading at the forefront of experimental physics owed much of the ability to draw essential contributions from his fellow workers. Young graduates and prominent scientists from around the world were drawn to work with him. He treated the most famous and the most juniors alike as equals. He was generous in giving credit to younger colleagues. Often, his name did not appear on papers covering important work which he initiated. His conversation was animated, and he inspired enthusiasm in others. The tone of his publications were tentative, never claiming more than had been strictly verified. Rutherford enjoyed the warm regard of people of many different nationalities and was capable of giving strong support to colleagues in personal distress. He is remembered alike for his breadth of humanity and his contributions to human knowledge. So, you said you learnt a bit in chemistry about Rutherford stuff.
Well, we were learning about the atom, I don't exactly remember what Rutherford did, but I'm pretty sure it had something to do with a model of the atom.
Yeah, that's right, Lee. So this video from Crash Course explains a bit about the model of the atom, in particular what Rutherford found about the atom.
How do you picture an atom in your mind? If you understand enough about atoms to visualize any of those things, then you know more about atomic theory than scientists did just 100 years ago. And like way more than they thought they knew 2,500 years ago. That's when Greek philosopher Leucippus and his pupil Democritus first came up with the idea that matter is composed of tiny particles. No one knows how they developed this concept, but they didn't think the particles were particularly special. They just thought that if you cut something in half enough times, eventually you'll reach a particle that can't be cut anymore. They gave these particles the name atomos, which means uncuttable or indivisible. So basically they thought that iron was made up of iron particles, and clay was made up of clay particles, and cheese was made up of cheese particles. And they attributed properties of each substance to the forms of the atoms. So they thought that iron atoms were hard and stuck together with hooks. Clay atoms were softer and attached by ball and socket joints that made them flexible, and cheese atoms were squishy and delicious. Now this makes a certain amount of sense if you don't happen to have access to electron microscopes or cathode ray tubes or the work of generations of previous scientists. Because the fact is, atomic theory as we know it today is the product of hundreds, if not thousands, of different insights. Some models, like that of Leucippus, were just blind guesses. As time went on, many more were the result of rigorous experimentation. But, as has been the case in all science, each scientist built on what had been learned before. Now you might think that once Leucippus and Democritus came up with the general idea of atoms, it'd be pretty easy for someone else to take that little indivisible ball and run with it. But you'd be wrong. The next major developments in atomic theory didn't come along for nearly 2,300 years. I've already told you, for instance, about the French chemist Antoine Lavoisier, who proposed the law of conservation of mass, which states that even if matter changes shape or form, its mass stays the same. And you should remember the English teacher James Dalton, who determined that elements exist as discrete packets of matter. Thanks to these and other great minds, by the 1800s, we had a better grip on the general behavior of atoms. The next logical question was, why? Why do they behave the way they do? This led to the investigation of atomic structure. In the 1870s, scientists began probing what stuff was made of using discharge tubes, basically gas-filled tubes with electrodes at each end, which emit light when an electrical current passes through them. It's basically what a neon light is. Because this light was originally produced by a negative electrode, or cathode, it was called a cathode ray, and it had a negative charge. But in 1886, German physicist Eugen Goldstein found that the tubes also emitted light from the positive electrode, basically a ray heading in the opposite direction, which meant that there must also be a positive charge in matter. Goldstein didn't fully understand what he'd discovered here. I mean, scientists still hadn't figured out what was responsible for the negative charge in the rays either. Then, English physicist J.J. Thomson took the discharge tube research further. By measuring how much heat the cathode rays generated, how much they could be bent by magnets and other things, he was able to estimate the mass of the rays. And the mass was about 1,000 times lighter than hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays weren't rays or waves at all, but were in fact very light, very small, negatively charged particles. He called them corpuscles. We call them electrons. So even though we didn't understand what shapes they took, we knew that there were both negative and positive components to matter. The next question was, how were they arranged in the atom? Thomson knew that the atom overall had a neutral charge, so he imagined that the negatively charged electrons must be distributed randomly in a positively charged matrix. And the very English Thomson visualized this model as a familiar English dessert: plum pudding, the positive matrix being the cake, and the electrons the random floating bits of fruit within it. Even today, Thomson's model of the atom continues to be called the plum pudding model. And while a single electron's motion is random, the overall distribution of them is not. The next big step was taken by New Zealander Ernest Rutherford in 1909. He designed an experiment using an extremely thin sheet of gold foil and a screen coated with zinc sulfide. He bombarded the foil with alpha particles, which he didn't really know what they were, just that they were produced by the decay of radium, they were positively charged, and they were really, really small. He expected them to just fly right through the foil with no deflection, and many of them did just that. But as it turned out, some of the particles were deflected at large angles, and sometimes almost straight backward. The only explanation for this was that the entire positive charge in an atom, the charge that would repel an alpha particle, must be concentrated in a very small area. An area that he called the nucleus. Because most of the alpha particles passed right through the atoms undeterred, Rutherford concluded that most of the atom is empty space. And he was correct. Rutherford would later discover that if he bombarded nitrogen with alpha particles, it created a bunch of hydrogen ions. Now, he correctly surmised that these tiny positively charged ions were themselves fundamental particles. Protons. Now we're getting close to reality. So these chemists had a fairly good idea of the structure of the atom, they just needed to figure out what exactly the electrons were doing. Enter Niels Bohr. In 1911, the same year the results of Rutherford's gold foil experiment were published, Bohr traveled to England to study with Rutherford. And as a physicist, he was also interested in the mathematical model set forth by German physicists Max Planck and Albert Einstein to explain the behavior of electromagnetic energy. Over time, Bohr came to realize that these mathematical principles could be applied to Rutherford's atomic model. His analysis of the gold foil experiment, calculations based on the proportion of alpha particles that went straight through, those that were slightly deflected, and those that bounced almost completely backward, allowed him to predict the most likely positions of electrons within the atom. Bohr's resulting model, sometimes called the planetary model, is still familiar to most people, probably including you. It represents the electrons in orbits around a small central nucleus. Each orbit can have a specific number of electrons, which correlates to the energy levels and orbitals in the modern model of an atom. And while it's definitely flawed, Bohr's model is very close to reality in some important ways. But like everyone I've mentioned in the past couple of minutes, Bohr was at once fantastically right and way off. The problem was those pesky electrons. It was the German theoretical physicist Werner Heisenberg who got everyone to understand just how huge and mind-blowing this electron problem was. But he was also the one who helped tie the whole mess up into a neat little bundle. Using his wicked math chops, Heisenberg discovered that it is impossible to know with certainty both the momentum of an electron, or any subatomic particle, and its exact position. And the more you know about one of those two variables, the harder it gets to measure the other one. So if you can't measure the position or momentum of an electron, you obviously can't say with certainty that the electrons in an atom are all neatly aligned in circular orbits. So he and a new wave of physicists and chemists proposed a new theory, a quantum theory, which proposes that electrons weren't particles or waves. Instead, they had properties of both and neither. By this thinking, the arrangement of electrons around a nucleus could only be described in terms of probability. In other words, there are certain regions where an electron is much more likely to be found. We call these regions orbitals. You know, the very same orbitals that you and I have been talking about. The ones that go by the names S and P and D and F and that form sigma and pi bonds. Those are the things that Heisenberg's theory predicts, and that's the modern understanding of atoms. Because it's based on probability, quantum-style atoms are often drawn as clouds with the intensity of color representing not individual electrons, but the probability of finding an electron in any particular position. For this reason, the quantum model is often called the cloud model of the atom. And now you know! All the people I've mentioned and many others put their heads together over time to build this current and, I might say, quite elegant understanding of atomic theory. Now, after 2,500 years, even though we can't see them, we can know what they're like and how they work because a long succession of scientists contributed bits and pieces to the whole fantastic picture. But it's also important to recognize that we still may not be quite all the way right. Thomson's contemporaries were sure that the plum pudding model was right, scientists in Bohr's day fully believed that the planetary model was right, and today we're extremely confident that the quantum model is correct. But it may not be all the way correct, and the only way we can go on being sure is to keep asking questions and conducting experiments.
Wow, that was really inspiring, wasn't it, Lee?
Yeah, that was some juicy science.
Yeah, Rutherford's just done so much for science and for the world. And, oh, what's the time now? It's getting almost midday, right? So you have to head off to work?
Yeah, it's almost 12 right now. And I start at 12.
Yeah, you've got a long shift ahead of you.
I do 5 hours of flipping burgers.
Yeah, just like SpongeBob did it.
Yeah, yeah, exactly, yeah.
Anyways, I better not hold you up for too long, Lee. Thanks a lot for coming on my show.
No problem.
And that's it from us. If you want to listen to any of my other shows, please visit my website www.questisfun.org.nz/youthvoices. That's quest-is-fun.org.nz/youthvoices. So, see you again next month on the first Wednesday at 2:10 p.m. Goodbye!
Bye!
Join me again for another exciting program next month on the first Wednesday at 2:10 p.m. or listen anytime online at planetaudio.org.nz/youthvoices or listen to the archive on my website www.questisfun.org.nz/youthvoices.
Youth Voices.